Thank you all for listening in. My name is Diego Rivera, a recent graduate of MIT in the United States, and as one of the recipients of the 2020 Hangai Prize, I've been given the honor to present this prize medal here. Now, as you might know, this medal is typically conferred in person, and while this conference is entirely virtual this year, my immense gratitude remains to the IASS, to the University of Surrey, and of course to the Hangai Prize Committee for selecting me as a 2020 recipient for this award. Dr. Hangai's participation in the ISS, his role as a mentor, and his involvement with the younger generation is truly inspiring, and I hope that I can serve as a similar role model for those aspiring designers who come after me. I'd also like to quickly thank my advisor, Dr. Caitlin Mueller, and Dr. Renaud Deneuve, who provided invaluable guidance and support throughout my graduate studies, and for that, I'm extremely grateful. Now, it's my pleasure to present my research in which I introduce a new adaptive optimization framework for the exploration and conceptual design of perforated patterned surface structures. Surface structures have been of interest to the ISS since its inception in 1959, and we know that when designed well, they can be highly efficient structures. But by strategically removing materials, such as through patterns, designers can create opportunities to integrate stimulating visual and lighting effects into an already elegant structural design. Naturally, though, certain pattern configurations yield better or worse structural performance, but we can use structural pattern optimization to try to find those that actually improve structural efficiency, saving material where it's not fully utilized, and in turn, creating a visual display of the flow of forces within the structure. This way, we can design efficient and compelling surface structures by means of subtracting material, a concept exemplified already by some beautiful structures around the world. But while these structures are truly inspiring and serve as wonderful exemplars for the idea, their design is undoubtedly complex, and they beg the question, how can we more efficiently explore these types of pattern structures and optimize for the best performing patterns? This served as my primary motivation for my research. Now, similar questions have previously been addressed in several different research fields. Specifically within the computer graphics community, the recent work on the integration of pattern design and structural optimization has a similar motivation, but generally focuses more on mathematical and computational processes and is a bit removed from the application to real-world structural engineering and architecture. And while recent advancements in digital fabrication have already demonstrated the ability to manufacture structures, such as those shown previously, the methods used for their design illuminate challenges associated with the use of FEM for the optimization of pattern structures, specifically the process of remeshing the analysis model between design iterations, which can drastically increase computational expenses during optimization. And in the end, there seemed to still be a need for a computational method that was fast, effective, and could be seamlessly incorporated within an accessible design framework. So my research aims to address this issue by building upon a more recent work published in 2018 that employs isogeometric analysis, or IGA, instead of FEM to perform structural analysis, thus taking direct advantage of the mathematical processes of NURBS geometries. At a very high level, NURBS forms the basis for geometric definition in most contemporary CAD environments. Important for the methods that I'll discuss shortly, NURBS creates a functional relationship between a 3D physical space in which NURBS geometries are visualized and a 2D parameter space in which the same geometries are mathematically defined using a set of basis functions. One of the advantages of IGA here is that it uses the same basis functions to carry out numerical analysis for structural behavior. So IGA can be directly incorporated into a CAD modeling platform and avoids the need for meshing the analysis models between design iterations, like in FEM. Now, to accommodate patterning on surfaces specifically, I used an improved method for trimmed IGA, as outlined in Deneuve and Mueller's 2018 work, in which a set of trimming curves that differentiates between void and solid is applied directly to the 2D parameter space of the surface of interest. This way, the 3D surface never actually needs to be physically trimmed, except for visualization, and it remains unaltered during optimization. Forming a basis for my research, these methods were then implemented in Grasshopper, through which a pattern optimization framework could be built around the trimmed IGA methods. And this framework operates in 5 main steps. First, defining the design surface that represents the physical structure to be perforated, or the analysis surface. In most of my examples, the geometry of this surface remains constant during optimization, although it's not a requirement for these methods. Second, defining the aperture pattern or set of trimming curves to be applied to the analysis surface, which is created separately over the domain of the analysis surface in its 2D parameter space. This is the pattern which will be optimized. Third is scaling the aperture pattern, which is performed by a control surface that is independent of both the aperture pattern and the analysis surface. And here, the control surface is generated over the aperture pattern and utilized such that the height of the control surface over each individual aperture, noted for example by the orange line in the center figure, defines the scaling factors for each corresponding aperture. As illustrated, the greater the distance, the larger the aperture. Now, one key advantage of keeping this control surface independent of the aperture's pattern is that it can be maintained across any aperture pattern and the scaling information is preserved. Using a NURB surface in this context also assists in optimization, for which the control points of this surface are the design variables. This is a technique used within my research group to decouple the number of design variables from the number of elements to be sized, and to simplify the optimization problem. So, going back to the general framework, the fourth step is now performing structural analysis using the methods previously described. And fifth, optimizing the aperture pattern by manipulating the control surface using a constrained optimization component that wraps a state-of-the-art optimization library. For my examples, the objective function is typically compliance, measured in terms of strain energy, while the constraint is the volume of remaining material. And at any point in the process, we can pause to visualize our designs. Now, while this optimization framework works in general for pattern surface design, it can be computationally expensive, taking up to a matter of hours to generate just one result. So one of my first efforts in my research was investigating the performance of these methods, looking specifically at two criteria: quality of the solution and speed at which it's found, which I looked at by conducting a series of computational experiments, for which I used analysis models of beams to study the influence of various parameters on the optimization process. And to summarize, we found that optimized designs found using low-resolution analysis surfaces behaved comparably to those found using higher-resolution analysis surfaces, and that the lower-resolution designs were achieved in just a fraction of the time. Similarly, with regard to aperture pattern density, we found that optimized designs found using fewer apertures were achieved in significantly less time than those found using more dense patterns. And importantly, regardless of the density of the aperture pattern, the general form of the optimized design was maintained, which compared well to topology optimized designs. So, in response to these findings, we proposed an adaptive framework that takes advantage of the quality of the low resolution results to speed up the optimization process. And this framework operates as follows. First, we start with a low resolution analysis surface and a pattern with relatively few apertures. Then we optimize the aperture pattern for the low resolution analysis surface, and we achieve a preliminary design. We then refine the analysis surface and the aperture pattern, but we maintain the same scaling surface from before. And we optimize the refined aperture pattern for the higher resolution surface using the same scaling surface from the previous step as a starting point for this refined optimization. And this process of refinement and optimization can be repeated as required, where the optimized scaling surface serves as a starting point for the subsequent step. To validate and demonstrate this framework, we applied it to a variety of conceptual design case studies. To start, the cantilevered canopy structure, which is fixed along its curved end and resists a downward load at its free end. Here, the surface geometry remains constant and the aperture pattern is optimized. We used a three-step adaptive scheme, and similar to the beam experiments, the general optimized form is maintained regardless of the aperture pattern density. Intuitively, the optimized designs form a 3D truss with a tension cord along the ridge of the canopy and two compression struts along either end. Comparing the results of the three-step adaptive scheme to that of a non-adaptive high-resolution scheme, the final optimized designs behave and appear very similarly. In this case, the results of the adaptive scheme perform slightly better and is achieved in almost half the time. So next, we considered an idealized form-found shell with formed pin supports. We applied three different aperture patterns, but held everything else constant. And the results differed for each pattern. indicating that the shape of the aperture patterns can influence the form of the final design, something of interest when considering visual and lighting effects. Next, we studied a flat roof subject to uniform loading and bending out of plane. Here we consider 3 different objective functions, and intuitively, we achieve 3 different designs. And we can see how these variations in material configuration influence the behavior of the overall structure, as illustrated by the magnified display shapes on the right. Lastly, we looked at a generic free-form shell for which we optimized surface geometry and aperture scaling simultaneously. Here, again, the final design reacts to the optimization problem, and we see variations in both the aperture patterns and the surface geometry using these methods. This research also illuminated several exciting directions for future work. The analysis methods could be further expanded to account for second-order effects and dynamics pertaining to shell mechanics, and from a fabrication perspective, exploring how the removed material can be repurposed or recycled could help address an important sustainability question. Now, to summarize this work's contributions, we presented a rigorous yet accessible computational method that integrates pattern design, structural analysis, and CAD modeling. Notably, we've demonstrated the speed and effectiveness of the proposed methods, and since the designs are generated within a commercial CAD environment, the resulting designs are readily fabricable. An important and interesting step forward in engineering design, this work offers yet another way to integrate architectural vision and structural performance in the early stages of conceptual design. And with that, I'd like to thank you all again for listening. It's been an immense honor to present to you all, especially with this kind of recognition, and I'm incredibly thankful for the opportunity.